Okay, good morning. Good morning to all.
Good morning, sir.
Okay, so we will continue from the place where we stopped in the last class.
Sir, excuse me, sir.
Yeah,
Sir, like when is the last day for uploading full DA in Teams, sir?
yesterday in Teams.
Yes, sir, in
Uh,
Teams. You say
Teams
I kept you
15th,
message, no, sir.
15th, 15th.
Uh, okay, sir.
Okay,
Thank you, sir.
Thursday. Okay, okay, fine. Okay, so we were discussing about that FDMA things. Then in FDMA we have, so this SCPC is the single channel per carrier, where each earth station has only one signal to send. It will frequency modulate it or PSK modulate. If it's a digital thing, they use PSK, and if it's a analog thing, they use the FM. So there is only a single signal which it is transmitting, FM or PSK. But in the multiple channel, what we have understood is the earth station itself can perform the multiplexing, either FDM or TDM, at its own end, and then combine all these signals onto a mega carrier and uplink it to the transponder. So in the multiple channel, earth station itself first performs the FDM or TDM and collects a large number of signals, and all of those signals are uh, remodulated onto a mega carrier and uplinked to the transponder. So these two were the schemes in the FDMA. Okay. So then there was some problem with the intermodulation. So whenever a nonlinear device is handling more than one signal, then we get this intermodulation products. So especially of much interest is the third order intermodulation. So we have taken the input output modeling for a non-linear device. So here this is the one signal A1 cos omega 1t, then A2 cos omega 2t was the another signal. Then output characteristic was like A into V in plus B V in cube. Although there is V in square also, but here it's not so important. So they have just concentrated on the third order term. And then the first term is a linear term which is used for amplification. So we don't have any problem with that. So actually that is the desired signal. This problematic term is only this B into V in cube. So we have put more focus on that and finally concluded that if two signals of F1 and F2 are coming, then the problematic terms are this one, 2F1 minus F2 and 2F2 minus F1, because they are third order intermodulation products and they are still within the transponder bandwidth. And since they are cubic terms, the normal power is P1 plus P2 desired power, undesired power is P1 cube plus P2 cube. So it's like more magnified, and we have understood that for each 10 dB or 1 dB increase in the signal power, it may lead to 30 dB increase in the intermodulation product. So if you have 1 dB increase in signal power, 3 dB increment in the IM products. So then here we have seen like what are the two types of transponders. One is the bent pipe transponder where only the mixing and amplification is taking place. Regenerative transponder is based on onboard signal processing, so it will, apart from amplifying and mixing, it will also recover the bits, and it will perform complete error correction and error detection and error correction, and then again it will retransmit the bits. Okay, so then yeah, so we will go for the numericals. So many numericals are there. So yeah, okay. So this is based on that intermodulation products, IM products. So what they are telling is a transponder has 36 megahertz bandwidth, and from where to where it is, that 36 megahertz is from 3705 to 3741. This is the 36 megahertz bandwidth which is allotted to one transponder. And by the way, in this C band, what they do is for each satellite generally Each satellite generally has a bandwidth of 500 megahertz. Overall satellite generally has a bandwidth of, so satellite having bandwidth is like comedy. So satellite does not have any bandwidth. The communication equipment on each satellite. Okay. So the communication subsystem on each satellite. So satellite does not have any bandwidth. Okay. So has generally 500 megahertz of bandwidth, and each transponder is like 40 megahertz including the guard band. So each transponder bandwidth is around 40 megahertz. So therefore, a satellite with 500 megahertz capacity, 500 megahertz capacity has 12 transponders, has 12 transponders. And if you make use of that polarization concept, polarization diversity, if you make use of, then using the same bandwidth, we can have 24 transponders. So frequency reuse is possible when you use the polarization, different orthogonal polarization. So within the same frequency, you can maintain two channels. One is through horizontal and the other one is through vertical. So there 24 transponders are there. And okay, so that is the basic information. Okay, so this is the 36 megahertz of the transponder. Now in this, what is telling, there are two carrier signals, two earth stations. Let us say where is three? Okay, 313718 is one earth station, ES1. Then ES2 is 3728. This is what the center frequency. Okay, so center frequency of first earth station is 3718, second earth station is 3728. Okay, so around that it will be some area will be there. It's carrier, means that is only a carrier, but around that there will be some bandwidth to modulate the message, right? So 4 megahertz this side and 4 megahertz this side, that is the bandwidth. So for the second earth station also 4 megahertz this side and 4 megahertz this side. So it's like just FM radio. So if you tell 93.5 FM, so 93.5 megahertz is their center frequency or the carrier frequency. But that alone is not sufficient to modulate their voice or audio. Some bandwidth is needed. This side 100 kilohertz and this side 100 kilohertz. Total 200 kilohertz bandwidth is needed for FM, including the guard band, but this centered at 93.5 megahertz. So that is the meaning. So if you give alone them carrier frequency, they cannot accomplish anything. So you should give them proper bandwidth also along with the carrier. Right. So centered around that frequency, you will allot some bandwidth such that they will modulate the signal and transmit it. So here also the same thing. Transponder is giving two center frequencies, 3718 and 3, what is that? Yeah, this one 3718 and 3. So then what is the question? Determine the intermodulation frequencies and verify whether they are within the transponder band. So intermodulation frequencies are 2f1 minus f2 and 2f2 minus f1. So that much knowledge we have. So here f1 is this one and f2 is this one. So how much is 2f1? So this is just calculation only. 3178 minus f2 is how much? 3728, and 2f2 minus this one. So this is, how much is this? 2 into 3728 minus 3718. So these are the intermediate frequency components. So what is this answer? So 2 into 18 is 36. 36 minus 28. 1606. Okay.
3708, sir.
No. Okay. 3708. Fine. 3708 megahertz is one. This 2F. And what about this one?
3738.
Okay, man. Thank you. You are a good person. Okay, so he's telling to verify whether they are within the transponder bandwidth. So 3708 is where it is somewhere here 3708, and 3738 is also within the transponder bandwidth. So actually, yeah, so these two are the intermodulation frequencies overall for the whole transponder when it is carrying two carriers or two signals. Okay, so then what is the problem? So is there any problem or is it fine? So now again, so this part is over. Overall transponder wise, it is over. Now it is the specific thing for this F1. So F1, if you remember, it is centered at 3718, and this side 4 megahertz 3722, and this side 4 megahertz 3714. Okay. So this is F1. This you can denote as F1 high, and this you can denote as F1 low. And similarly, the other carrier F2, F2 is centered at 3728. So 4 megahertz this side. Sir, how come you are getting this 4 megahertz? Is it will be given in the question, like each signal, each carrier has a bandwidth of each signal, or each earth station is allotted a bandwidth of 8 megahertz. Allotted a bandwidth of 8 megahertz around the carrier. So 4 megahertz this side, 4 megahertz this side. So 3732 here, this side 3724 here. So this is F2 high, this is F2 low. Now what he's telling is, even for this earth station frequencies, they will also interfere.
Saat game is
Okay. So the overall intermodulation products were those things, but within the transponder or within the each signal also there will be intermodulation products. So the frequency or the formula for that is 2f1 low minus f2 high. So this is for the first earth station. Basic formula is same thing, 2f1 minus f2 and 2f2 minus f1. So here low to high and high to low. So like from this low till the second one high, okay, till here, and then second one high, on first one high to second one low. So basically the same formula you have to remember. So now calculate this 2f1 low. 2f1 low is 3714. Here f1 low minus f2 high. F2 high is how much? 3732. So this is one frequency. To second one, this one 2f1 high. 2f1 high is 3722 minus f2 low 3724. So two times here. So what are these values?
3696 to 3720.
3706
No,
to
sir. 3696. Sir, first one is
3696. Okay.
3696.
Okay.
3696 to
Because it should be within this range 3705 to 3741.
Sir, but the calculation is coming out 3696 only.
Yeah, just let me see. Okay. Okay, so what they have done in the question, they have taken 3728 itself, but in the answer they modified it as 3730. The second carrier's center frequency is 3730. So based on that, this is 3726 and this is 3734. So based on that, so we can change in the question also. 3730 is the second carrier. Okay. So based on that, okay, anyway, you tell what are the values you are getting. 3696 and
3720.
3720. Okay. Then what about the this second value? 2 into F2 low is, we will go with our values only. 3724 minus F1 high. F1 high is 3722. 2F2 high. 2 into F2 high is 3732 minus F1 low. F1 low is 3714. Okay. So what we do generally is we will again draw a diagram like overall diagram from here to here. So this is the overall transponder bandwidth 3705 to 3741. So one carrier is at 3718 F1 and another carrier is at F2 3728. Then these are the desired components, 4 megahertz this side, 4 megahertz this side. And if you see what are these values, 3724, so this is 48, this is 22, so maybe 3726.
3726.
Okay, 3726, this is 64 minus 3750.
Yes.
Okay, fine. So actually now this can be treated as 3696 to 3720. So 3696 is somewhere here. So from here to 3720, this is the first intermodulation product for the first earth station. Then 3726 to here 3750, it is the intermodulation product of the second earth station. So if you see These have, so these intermediate products have bandwidth of 2b1 plus b2. So this is 2b1 plus b2, that is uh, 2 into 8 megahertz is the bandwidth of first star station plus 8. So totally 24 megahertz bandwidth will be there for this intermediate modulation product. So here 96 to 20 is 24 megahertz. So here also 24 megahertz. So now this is how they are present. So if you see the desired area also they are occupying. So the desired area is around this carrier frequency. This part they are occupying, and also here they are occupying the desired portions as well as the god bands also they are occupying. So it is very difficult to get rid of them. Yeah. So I think in the textbook there is some calculation mistake. So in the starting they were assuming 3728 and suddenly they have gone for 3730, and then all these have come in within this range. So actually that second edition of Timothy Pratt has a lot of mistakes, typing mistakes as well as uh, concept mistakes. So yesterday I was asking you, one of you has told here a plus b whole cube, a cube plus b cube, 3ab square, 3. So something they have told like 3ab into a plus b. So that was fine, but in the textbook they gave only 2 here and 2 here. So like that, gross mistakes are there in that version, but somehow in the new version, 2020 version, they have corrected all that. Okay, so overall, what we are trying to do here is we are trying to say that these intermodulation products occupy well within the transponder bandwidth, and they try to disturb our filtering aspects. So if we try to filter out only our desired signal, then this IM products will also come out of that filter, like they won't be eliminated by the filter. Okay. Okay, fine. Yeah, so this one, since they changed that second carrier, they put it as 3730. So due to that change, all these IM products are occupying within the transponder bandwidth. So here in the second part of the question, they considered three carrier 2 has frequencies 3726 to 3734. So that's how they got this one. Okay, but the overall concept is same. So then what we have to do to overcome this, we have to apply output power back off. So power back off is we should not operate the amplifier at its rated output capacity. We should operate below the threshold. Like if the rated power of transponder output rated power is 100 watts, so we should not operate it at 100 watts. We should back off a little, like we should operate at 70 watts or 67 watts or 50 watts, so that we will get some additional dB of back off. So like instead of operating 100 watts is how much? 100 watts is in dB 10 log 100. So 10 log base 10 100. So this is 20. So instead of operating at 20 dB, if you little bit back off, so 50 is too much, but at least if you back off till 70 or 67, so we will get some dB of output back off. So if you uh, compromise like this, like instead of operating at the rated capacity of the output, if you just operate it little below, then you will get 3 dB improvement. And he says that when you back off 3 dB by for the linear signal for the amplification, the intermodulation products will reduce by 9 dB, which is a good reduction. And whenever you are backing off by the output, So to produce that much output, even the input will be backed off. Like after all, amplifier is what characterized by gain. So gain is V naught by Vn. So if you don't want a large output, if you are backing off at the output side, then the input will also be backed off. So that will be the input back off. And here he says that it's not linear, so more input back off will be obtained. So for every 3 dB, generally 3 dB output back off, we expect 3 dB input back off, but here due to the non-linearities, we get more additional input back off, which is a good thing. You need not supply more power at the input of the amplifier. Okay, so these are the things which are needed to overcome this intermodulation products. So in FM, FDMA, this is a big problem. So so there is a question like why back off is applied only in FDMA systems and not in TDMA. So only in this FDMA we are characterizing each earth station using the carrier frequency, and transponder has to handle many signals from different earth stations which are at different frequencies, and therefore this intermodulation problems will occur, and therefore we have to back off the input and output. But in TDMA, all the stations are occupying the entire bandwidth of the transponder, and there are no particular carrier frequencies. So we don't have this intermodulation problem in the TDMA. So then, how does this TDMA frame structure look like? So frame structure is like generally you have some what is that overhead over control overhead, that is called, and followed by the actual data bits. So any frame has some control overhead. So control overhead is like you have some bits for synchronization and some bits for error recovery, some bits for identification like flag. So if you have a flag there, 0 1 0 1 1 1 1 0, so then the receiver understands that from here the frame is starting, and accordingly it will process the packets or frames. Then we also require flag or preamble. So preamble, then there is some information about the clock recovery. So since in the TDMA it's everything based on the common clock, we should have the mechanism for clock recovery also. And so this is the general frame structure we will see in detail. But what is frame efficiency in TDMA? So what is the frame efficiency is given as maybe eta. So 1 minus t overhead frames by actual data frames. So it's like out of 100 bits which you are sending, let us say there is only 10 bits, sorry, only 90 bits are corresponding to the actual traffic or the actual data which you have, and these 10 bits are acting as a overhead. So overhead is like there are some bits for synchronization, there are some god bits are there. So we told in TDMA we need to leave some interval between the successive what is that symbols from each earth station or from each user. So because of that it corresponds to some bits, so those are the god bits, and then you have the synchronization bits and preamble and all these things. So those are all called as overhead. They are not actually contributing to the message, but still they are needed. So what is the frame efficiency now? So 1 minus what is the overhead? Overhead is 10 bits, and what is the this one 90. So 80 by 90 is the frame efficiency. TDMA frame efficiency. So you cannot, so though you know that you should have a high frame efficiency, so you should not waste many bits within this overhead, but you cannot do it as such. So Like this god bit should be there, proper amount of god bit should be provided in order to overcome the propagation delays or the inter symbol interference. And similarly, this clock recovery and synchronization, they should also be given enough number of bits so that the receivers can recover the proper information or the exact clock information. So it's not like see, in a simple, suppose if you have 200 bits in a bit stream, and suppose the starting is from the fifth bit. So instead of that, let us say the receiver is understanding, or there is no sync between the receiver and the transmitter. It has thought that from the sixth bit next frame is starting. So it will decrypt or decode this frame from the sixth bit, and it everything will go wrong, right? So like first 8 bits will be for the flag, so then it will understand these 8 bits are for the flag, then the next 8 bits may be the message of one earth station, after that another earth station, so everything will go wrong during the decoding process. So exact time synchronization is very essential in the TDMA. Okay, so then what are all there in the TDMA frame? So there are two main types of frames in the TDMA. One is the reference burst and the other one is the traffic burst. So reference burst, as the name indicates, it is for reference information, and the traffic burst is the one actually which carries the information. So how do they look like? So carrier, clock recovery, then unique word, unique wire channel. So you need not really worry about all these things, but for a general understanding, I am giving you all these things. Then transient timing control, timing channel. So this is the starting of the reference burst. So all these are called as preamble. And from unique wire channel to here, it is called signaling channel or control bits. Okay. So then what happens in the data burst or in the traffic burst? So carrier and clock recovery, then unique word, order wire channel. So order wire channel is whatever the order has to be given from the earth station, whatever the command has to be given to the transponder, that will be coming in this bits. Service channel, then information subburst 1, 2, 3, like that. Information subburst 2, and so on. Information subburst n. So here this is the traffic burst. So the structure is for the traffic burst or the traffic frame, and here the first three things are called as preamble, and these two are called as the control bits. Then after that, okay, after the service channel, from here to last, it's all the traffic bits. So overall, what I want to tell you is what are the things which are there in the reference burst. And so reference burst will have in the reference burst we have carrier and clock recovery unit 1, then unique word we have, then order where channel we have. So these are important when you want to solve the numericals. Management channel is there, then transmit timing channel. Okay, so these five are there in the reference burst, and in the traffic burst what we have, you have this carrier and clock recovery, you have the unique word, then you have the service channel, then you have the information subburst. Okay, so these are all available in the traffic channel. So then based on that, so they are trying to ask us what is the efficiency of this. So overall they have given the frame length 20 milliseconds, then carrier and clock recovery bits are these many, unique word is this much, all these are given. So then 10 stations are transmitting and two traffic birds. So all the details are given. So we have to calculate how much is the efficiency, how much is the length of the preamble, all these things. So length of the reference bus preamble. So you should know what are there in the preamble of the reference bus. So carrier, this one is there, unique word is there, unique wire channel is there, see unique wire channel, order wire channel, all these things are there. Then in the preamble of this one only three things are there, so based on that you have to calculate. So I don't think now we can do it, but I will show you overall what is going on in this TDMA. So basic thing in the FDMA was that problem with the, what was that, intermodulation, and in TDMA main problem is the synchronization. So if you see this TDMA, so we know that each earth station will send in turn, so they will share the transponder bandwidth on the time sharing basis. So each earth station will be allotted a time slot in which it has to transmit. So the frame structure will be something like this. So typical TDMA frame structure will have reference burst and traffic bus from different at the stations, and in between we each burst will leave some guard time. So inside this reference burst what is there, that I have drawn previously, and similarly within each traffic burst what is there, there is some preamble and some information. Within the preamble you have carrier and clock recovery of that earth station, unique word for that earth station, signaling channel, then its own traffic. So what is there in the reference burst? What is there in the traffic burst? Why guard time is needed? What is the structure of the TDMA burst for the reference burst? What is the structure? And for the traffic burst, what is the structure? And then this probability we don't want. So this, he says that unique word is very important and it has to accurately detected without any bit errors. So for that there is some amount of protection for those bits, so additional protection is given. So then the frame efficiency, and so how this control and coordination takes place. So all this is not needed actually for you, but only the overall essence you have to understand. So how do you acquire the frames and how do you perform the synchronization? So this frame synchronization, as I told you, so if it's starting from the fifth bit, you should be ready at that fifth bit. If you are at seventh bit or something, or if you are lagging, you are thinking it is from third bit, then it causes timing errors. So here they have given an example. Due to the variation in the orbit and inclination, so there will be some amount of errors, and it will lead to, due to this range variations we get a error of 40 nanoseconds per second. So So what is this nanoseconds per second? So generally the overall delay variation will be 1.15 milliseconds, and within 8 hours it is moving from the nominal position to the place where there is maximum variation. So all this in the numericals we will see what is the effect of all this. So basically even these minute variations in the range, inclination and orbit of that satellite will cause much variation in its in the signal propagation delay. So therefore we should be exactly sure of frame synchronization and where the things are starting. So otherwise it will be like that. This kind of errors will happen. So if it's starting at the fifth bit next to frame and you think that it is starting at sixth bit or at this timing, so then everything goes wrong. So we have to be very strict in the very tight synchronization is needed. Okay, so after this I will show you what all we have. Few numericals of the TDMA, finding out all how many bits are needed for each of these things. Then if that much bit length and all that is followed, then how much data rate you can obtain and how many voice channels you can support, and how much of this range, altitude and orbit variations, how do they influence the TDMA calculations, this problem. So then we go to the CDMA and how the signals are recovered in the direct sequence spread spectrum when all of them are at the same time and same frequency. So then CDMA numericals, then how CDMA is used in GPS briefly. So these are all the things which I want to cover. Okay, so I think now time is over. I will stop here. So now